is tired and it is Friday, and it's a dreary Friday, which is not the best, but hopefully pleasant weekends are ahead for us all. All right, we've been discussing momentum as of late. Plan for today is to look at an elastic collision example and talk about what works for those, that doesn't work for inelastic. And at the end of class, we're going to talk a bit about gravity as kind of a segue into what we're going to discuss next week. How do you guys feel about any of that? And do you have any questions about anything at all before we get started?
So, do you think if we've already got the homework done, do you think we can move on to the quiz?
Yes. Yes. All right. So between lecture and lab, we talked a bit about the differences between elastic and inelastic collisions. Primarily, we've done so through momentum, but you can also analyze them through whether or not kinetic energy is conserved in that type of collision as well. Momentum is conserved in all types of collisions because it has no other form it can occupy, so that's true of both. What's different between both is that kinetic energy is lost in inelastic collisions because the objects involved tend to absorb energy and change shape, and then they don't give it back because they can't go back to normal. Whereas in elastic collisions involving elastic objects like springs and rubber and basketballs and stuff like that, those being elastic are able to absorb energy and then give it back. So kinetic energy tends to be maintained in those types of collisions. As a result, they tend to be more energetic, things tend to bounce off of each other in lots of different directions, and even though momentum is still conserved, that is still true. Kinetic energy is just conserved alongside of it, which actually means that elastic collisions, as chaotic as they are, you have more options with how to work them. So, as I mentioned, you should pay very careful attention to whether a problem tells you if a question tells you if the collision involved is elastic or inelastic. You need to look for that keyword before you know whether or not momentum is your only option or you have some other alternatives. To demonstrate those alternatives, that's not the slide that's supposed to be up. There we go. Again, inelastic momentum is the only thing conserved, and therefore comparing initial momentum to final momentum, like we did last time for the throwing star colliding with that log, that is your only option for inelastic. But for elastic, because kinetic energy is also conserved, you could compare the total kinetic energy levels of the system both before and after the crash. Additionally, as an additional method of working these elastic versions instead, some very smart people kind of took these two approaches and hybridized them to create this third option. So this is a third alternative for working one-dimensional elastic collisions. It only works elastically, and it only works if the questions are one-dimensional in nature. Those are the only type I plan to give you, so that's kind of a moot caveat for this particular class. So don't worry about that necessarily for here. 1D collision just means things are moving only forwards or backwards in a single axis, and those are the types of collisions I plan to give you. So on your formula sheet, these three separate lines represent ways you can analyze collisions, but these two only work elastically. Which again means you should read the question to check for that keyword. Now, we're going to look at a rather extreme and kind of silly case of an elastic collision. one, to kind of show that all three of these methods work, and two, to demonstrate why you don't want a car crash to be an elastic collision. So here we have two fairly famous talking cars that are going to drive headlong at each other. They're two different cars from various sci-fi properties. This talking sports car is called Kit. It's the car from a show called Knight Rider from many, many moons ago. Actually, no, they rebooted it a decade or two ago. Point is, it's a sports car, and it can drive itself, so no humans are involved in this example. And that sports car, before any sort of a collision takes place, is going to be driving forwards at 45 meters per second. So here is a very poorly drawn sports car. Mass of 400 kilograms, driving forwards at 45 meters per second. And this highly advanced sports car is going to be driving towards a very large truck. The biggest talking self-driving truck I'm aware of, at least that's a villain in the show it comes from, is Nemesis Prime from Transformers. I'm just a nerd. The names don't really matter. The fact is we have car set against truck. And the truck has a much larger mass of 2,000 kilograms. And they're both flying at each other head on at the same speed, but different directions. Directions is important to note. This is the before state of the collision, because all collisions have a before state and an after state. So this is all of our initial conditions, and I will label them as such over here. We've got mass, Kit is 400 kilograms. Velocity initial Kit is 45 meters per second, forwards. Mass, Nemesis Prime, is 2,000 kilograms. Velocity initial Nemesis Prime, 45 meters per second, but in the opposite direction. Again, that will be important. Velocity and momentum are both vectors. This is all our initial conditions. I've labeled the velocities initial for that reason. After the collision, after they collide, Nemesis is now moving at 15 meters per second in the same direction as before. What is Kit's final velocity after an elastic collision? So, in our after state, the big truck has slowed down considerably. Same mass, but greatly reduced final velocity. And we do not know Kit's final velocity. But based on your understanding of physics and your expectations from observing the universe your whole lives, what direction do you think the sports car is going to fly in after this interaction? Backwards. If this was even if this was an inelastic collision, I guarantee this car is going to turn around, because odds are it's going to end up pancaked on the grill of the much larger vehicle, and they combined will continue this way at a reduced speed. But this is an elastic collision, meaning that sports car is likely to bounce off at incredible speed, which, again, if you were a human in there, you would not want that. So we do know velocity final Nemesis Prime, 15 meters per second. In its original direction, I'm likely going to call these negative numbers. Just, again, they're opposite this one. One of the sets has to be negative for that reason. And our current unknown is velocity final Kit, velocity final sports car. And we're going to demonstrate the numerous different ways you can work this elastically. Questions so far? All right. So, we're going to show the three different methods very quickly. We're going to start with the one that always works. That's comparing the initial total momentum to the initial total momentum to the final total momentum, excuse me. So first we would need to find out how much momentum is in this system before the crash, and then separately, how much momentum would be therefore in the system after the crash. Much like before, these initial and final are both comprised of the two different initials being added together and the two different finals being added together. In this case, that would be momentum initial kit plus momentum initial nemesis equals momentum final kit plus momentum final nemesis. And for each respective momentum, you would use the respective velocity alongside of it. Kit's initial velocity, nemesis's initial velocity, kit's final velocity, nemesis's final velocity. So for each individual instance of the momentum formula here, one would need to plug in the relevant mass and the relevant velocity for that particular entry. So for kit's initial momentum, that's kit's mass times kit's initial velocity. For nemesi, for the truck's initial momentum, that would be the truck's mass times its initial velocity. Note again, the two vehicles are moving in opposite directions, so one of these two has to be set as a negative number. Velocity is a vector, momentum is a vector, so that is important. I have just arbitrarily decided that the truck is heading in the negative direction, just based on typical XY coordinates. You can very easily reverse that, but if you reverse that, then everything pointing left would need to be positive and everything pointing right would need to be negative. Here, I'm going to have everything right positive and everything left negative. Bless you. Again, you can flip that, but you have to pick one and be consistent with it. On the final side, it's the same two masses, but we use the final velocities instead. Again, the truck's final velocity is in the same direction as its initial, so that is also a negative number. How do you feel at this step? Now, what's nice here is we do know one of the two final velocities. Elastic collisions get kind of chaotic, so having this information makes things easier for us. VF for Kit the sports car is the only unknown left, so all we have to do is keep progressing our algebra until we can solve for that. There is going to be some fairly large numbers here because it takes a lot of momentum to make a semi-truck move. Solving for Kit's initial momentum, 400 times 45 gives us 18,000. And then separately from that, Nemesis's initial momentum, 2,000 times negative 45. Is negative 90. Yes, 1,000 momentum. The negative just indicates direction, so it's not that Nemesis has less momentum than Kit,
It's just that Nemesis points to the left. This means that as a whole, the system's total initial momentum is leftward pointing because the truck is bringing more momentum into the system, same speed but a bigger mass, and the truck's momentum points that way. So overall, the system's total momentum points to the left. The center of mass of the system as a whole is advancing leftward. That's kind of a good hint that Kit is going to lose this fight. On the after side, 400 times unknown, we will leave as is. And then there's Nemesis's final momentum, 2,000 times negative 15 instead of 45, that is only 30,000. Once again, VFK is the only unknown, so all we have to do is get it by itself. Just takes a few more steps of algebra. 18,000 minus 90,000. I'm also going to bring this over to the other side, so that would end up being plus 30,000. We put a final score of negative 42,000 on the left, set against 400 times VFK on the right. Divide by 400. Yikes. And that puts Kit's final velocity at negative 105 meters per second. Note, again, vectors, directions are important. The fact that this answer is negative and very large means not only did the truck hit the car hard enough for the car to come to a complete stop, it went from 45 to 0, there was still enough force left over to send it from 0 to 105 backwards. If this was not the most advanced sports car that 80s TV could come up with, it would be a pancake, a metal pancake. Even still, it probably is a metal pancake. Questions about arriving at this answer this way? Yes?
I just had a question in general. I'm sick right now, so I was just seeing if I can leave.
Yes. Yes. Attending class is never absolutely required. Please go rest.
I just didn't want to work out.
You watch the recording when you feel up to it.
Okay, thank you.
Always take care of yourself. If you are sick, stay home.
Thank you. Have a good week.
You too. Any other questions? All right. Now, that's the momentum method, which again always works regardless of collision type. I'm going to quickly kind of show how the other two methods would also work, just very quickly. Because since this is elastic, we can do the same thing we did with momentum, but with kinetic energy instead. I'm just going to work through this quickly just to show that it works, because there's more numbers involved this way. Using kinetic energy, you'd go through the same exact process, except you'd be using the KE formula instead of the momentum formula, but it's still the same masses and still the same velocities. So that doesn't change. It's just a question of there's a 1/2 on the front, the velocities are squared instead. Although as a result, it does tend to make the numbers bigger. It makes writing them down kind of a pain. using the same numbers, we can find the kinetic energy of each vehicle at every stage of this process. It is, it is worth noting, one, there's a lot of energy involved in this crash. There's over 2 million joules in the truck alone at the start of things. Two, note none of these numbers are negative, because energy is not a vector. Bless you. You square all the velocities, the direction goes away. Bless you again. As a result, all of these energies end up being positive numbers. Because again, energy doesn't care what direction you're going in. It just wants there to be a lot of energy involved in the crash and for everything to go flying everywhere. So the energy method, I don't use it as often because the numbers just get kind of ridiculous. But you do end up at the same final answer. Still get 105 out of it. That said, because again, energy doesn't care about direction, this method is flawed in that it actually does not tell you the sign of your final answer. It tells you the speed at which the sports car will bounce away, but it technically doesn't tell you that it turns around. So while the kinetic energy method does work, it is not my preferred approach. So I would not recommend it as much as I'd recommend the momentum version. But that third method that I showed on a previous slide, whoops, this last one down here that some very smart people came up with by combining the previous two methods, this is the easiest version of all. Because you don't even need to know the mass of the objects, really. This is just directly comparing the velocities involved of every object in this one-dimensional collision. So I'm going to do this one more time, proving this is the fastest way to do it. This formula says velocity of object 1 initial minus velocity of object 2 initial will equal, and the order in which these are written is very important, velocity of object 2 final minus velocity of object 1 final. Note they switch positions front and back on either side. That does matter for the case of the subtraction. So one more time, plugging in the same known velocities to try to prove again that we can get the same answer for the final speed. 45 for Kit's initial velocity, negative 45 for the truck's initial velocity, negative 15 for the truck's final velocity, and unknown for the car's final velocity. This would give us positive 95 on the left equals negative 15 minus V1F. Negative 15 comes over as positive 105 equals negative V1F. V1F would be negative 105. 3 different ways to arrive at the same answer. Out of all of them, pick your favorite, as long as it's an elastic collision. I go for this one when I can. There's no multiplication, or little to no multiplication, whereas the momentum formula, you have to multiply masses in. So again, to review, the big asterisks that should be in your notes. If a collision is inelastic, this is your only option to analyze it, because momentum is the only thing that's conserved. We proved that this works for the log, the inelastic one. We proved it works here for an elastic one. If it is elastic, you have 3 choices between these 3 cases. Out of all of them, as long as it's elastic, I'd first recommend this last one down here, then momentum, and lastly KE if you absolutely need it. The issue with KE is it takes longer and it doesn't tell you direction. How you guys feel? elastic ones, I'd say, are the tricky ones, because the fact that there's choice means there's more room to choose the wrong thing, unfortunately. And sometimes it means that the numbers involved get a little more chaotic. So I prefer the inelastic ones most of the time. But again, the main thing you should pay attention to when working a question is elastic or inelastic. Now, since momentum works all the time, you can just brute force it with that, honestly. But you should still pay attention to what all the information it gives you. And I encourage you to be working on the Chapter 3 homework over the weekend, and on Monday, any issues that come up, we can spend time looking at example questions together. Now, that's all of the momentum information covered. Any other lingering questions or issues at this particular time?
So is this the last bit of chapter 3?
Almost. The textbook does lump a small amount of universal law of gravitation into chapter 3. And since we have a minute, I'm going to talk about it now so that we can use it next week. So I do have one more thing I want to go over today. And this would also be, like, one or two questions about this would be factored into chapter 3 homework. So again, while working on it, if gravity stuff doesn't make sense, please let me know. We'll work on it on Monday in addition to what we say today. Always work on homework and bring questions to class. Did I address your concern? Okay. Anything else for this exact moment? All right. Now, think of this as a segue that will transition us into the new stuff we cover next week. We have talked about gravity in the past. It's a force. It's always going to be acting on you as long as you're on planet Earth. But the thing about gravity is it is not uniquely a force that exists between you and this planet. It is actually a force that exists between any objects with mass, any two of them. As long as two things are made of matter, no matter how far apart they are, there will be some gravitational force between them. It's just that the most massive object near you is the Earth, and so the strongest gravitational pull you will experience, assuming you never leave the planet, is that of the Earth on you. But all matter, as long as it has a mass, all matter has to be made of mass, as far as we understand it. So as long as something is made of matter and has a non-zero mass, it will have a gravitational attraction to every other object with mass. So right now, there is a gravitational pull between this marker and my hand. I don't have enough mass to pull the marker towards my hand with gravity, nor did I pass Jedi school. So, once again, the only gravity you will meaningfully feel is that of the Earth on you. Technically, the moon would be the next strongest from your perspective, and technically when the moon is right overhead, you are slightly lighter than normal, because the gravity of the moon pulls up on you, like how it pulls on the tides, but I don't think the human body is in tune enough to notice it. But it may make the hairs on your arm twitch. So, to understand how gravity acts between all objects, we have this new formula. And if I ever ask you how to calculate the force of gravity, spoiler alert, I always ask on test 1, how do you calculate the weight of an object? That's why I've been very particular to make sure you know that mass is not the same thing as weight. If I ask you how to calculate the weight of an object, you do not answer mass, you answer either m times little g, or you answer this. M times little g is the answer to calculate the weight of an object on planet Earth. But that depends on you being on planet Earth. This is called the universal law of gravitation, and it works between any two objects, even if one of them isn't a planet. You can use this to calculate the force of gravity between any two things, no matter what their mass is, and no matter how far apart they are. Because the distance between two things does affect that force of gravity. It's why you will never notice the effect of Pluto pulling on you. But Pluto does technically pull on you. It's just very weak because it's very far away. And it's a very small Plutoid. Now again, in physics, we like to use math as a language. So I'm going to look at this formula and I'm going to tell you what all the bits in it mean and how they affect gravity. Now, when I say universal law of gravitation, I refer specifically to this formula, like how Newton's second law refers to F equals ma. So that is just the name of this particular string of letters. And this formula tells us the force of gravity between any two things is equal to big G. This is not the same as the small g that we use here on planet Earth. Lowercase g, negative 9.8, is the acceleration of gravity from Earth on something when that thing is on Earth's surface. That does not work if you are not on Earth's surface. So technically, if you're in the atmosphere or even burrowed beneath Earth's core, burrowing towards Earth's core, negative 9.8 isn't even true anymore. So for any position other than on Earth's surface, use this formula instead. And instead of that lowercase g, this big uppercase G represents something else completely. This big uppercase G, is called the universal gravitational constant. It is a free number that you never have to memorize. It is written on your formula sheet. And it's just a constant that is required to make this formula work. Think of it kind of like how you need a coefficient of friction constant to make the friction equation work, but instead of a bunch of different ones, there's just one of these. And it's always this number, it's on your formula sheet, so you never have to memorize it, it's just a freebie as part of this formula. It's just a number needed to make the formula work. So, force of gravity between any two objects depends on the masses of the two objects multiplied together. This is why the mass of something determines how much gravity it creates. Because the more mass something has, the bigger the number that goes here, the bigger the number you get out on the other side. Again, two very small objects don't create a whole lot of gravity acting on each other, but the more mass something has, the bigger a gravitational field it creates. Therefore, it creates a stronger effect when it interacts with the gravitational field of another object. All objects with mass have gravitational fields, even very teeny tiny ones. Even single atoms, technically, have gravitational fields. And the more massive the object, the bigger its field, the more gravity it generates. So, the mass of the two objects matters, and then separately, how far apart they are matters. Once again, the sun's pretty big. Like, the sun creates a lot of gravity, but it's also very far away. So that, combined with a few other factors, is the reason why you are not being pulled into the sky towards the sun off of Earth's surface. Earth's force is more impactful on you because you are closer to it. Note here, not only is r squared, but r is on the bottom. Meaning that if r gets bigger, you're dividing by a bigger number and the force of gravity gets weaker. Meanwhile, if r gets smaller and you divide by a smaller number, you get a bigger force. So, in general, the two things that affect gravity are the masses of the two objects attracting each other and the distance between them. Namely, the distance between their centers of mass. That is one small caveat. Because if I asked you, how far apart from the Earth are you, what is the first number you might answer? 0. You're on Earth, right? But 0 is not what you plug in there, because if you did, suddenly you get a 0 for force of gravity, and we know that's not true. So that formula doesn't call for like the distance between your feet and Earth's surface. It calls for the distance between Earth's core and your core, your centers of mass, since Your mass is what's creating the gravitational field. So if you were to use that formula to calculate your weight on planet Earth, you would not, again, plug in a zero radius because you're on Earth. You would plug in Earth's physical geometric radius, because that's the distance between you on the surface and the center of the Earth. Which should, again, tell you, if you burrow down into the planet and that radius shrinks, the force of gravity is bigger. And that's why the core of the Earth is molten and pressurized in a place you don't want to be. The gravity down there is so insanely strong that it crushes rock into lava and then eventually crushes it back into solid iron. Again, gravity is stronger the closer you are to the mass of the Earth. How do you feel about the formula so far? I would like to briefly try to demonstrate it very fast. First, a very benign case. Let's say that we have two 1 kilogram weights. We've used 1 kilogram weights in lab before. I realize I don't actually have any in the room. So let's just say these are two very dense markers and they are 1 kilogram. And let's say they happen to be 1 meter apart. So this is not a scale. We could use the formula to find the force of gravity between these two things. Do you think it's going to be a very big number? No. That is a totally valid expectation. Force of gravity is big G times the two masses over radius squared. So for these two objects, big G is 6.67 times 10 to the negative 11th. The masses are each 1 kilogram, and I have placed them 1 meter apart. I used ones on purpose. And since I used ones on purpose, the answer comes out to be 6.6 repeating times 10 to the negative 11th newtons. That is a smaller force than the human nervous system could ever perceive. I don't even think that's enough force to make your arm hairs twitch. So again, you don't notice the gravity of the everyday objects around you. Even that semi-truck from earlier doesn't create enough gravity for you to notice. Because like 2,000 times more mass, it'd still be times 10 to the negative 7th. Things tend to get wackier on the galactic scale. So here we have the moon orbiting the Earth, much bigger masses. Frankly, the moon's big enough to be its own planet if it wasn't orbiting anything. The moon's bigger than Pluto. So we can use the same formula to figure out the force between the Earth and the moon. We use the same 6.67 times 10 to the negative 11th, but we plug in these much bigger masses. The moon is 7.36 times 10 to the 22nd kilograms. Bigger than anything on Earth except Earth itself. Speaking of Earth itself, we believe Earth's mass to be 5.98 times 10 to the 24th kilograms. Kind of weird that Earth is only really about 100 times more massive than the moon. And the distance between the cores of those two objects does actually fluctuate, but we're going to use the generally accepted average of 384,000 kilometers. However, all of our formulas like meters instead of kilometers, so I'm going to multiply that by 1,000 to make it meters, and then we're going to square it. So all the numbers here are, scientifically speaking, kind of wacky. have to be real careful punching them into your calculator. Final answer for the force of gravity between the Earth and the Moon is 1.99 times 10 to the 20th newtons. It's a lot of force. And frankly, these objects are pretty dang far apart. The masses are just so big that it's a lot of gravity regardless. For a small sense of scale, if that's Earth, and these are Earth's satellites, the moon lives there. The moon's pretty far away. That's why getting to it is kind of tricky. It's the next closest thing, but it's still kind of far. Which is good, we don't want it hitting us. And this tremendous amount of force is constantly acting between the Earth and the moon. An important caveat of this formula is that it acts in both directions. The Earth pulls with this force on the moon, pulling the moon towards Earth, and simultaneously, the moon is exerting the exact same force towards itself on the Earth. So whatever numbers you get from these formulas, each object is exerting that force on the other. It's happening both ways at the same time. Newton's third law, action-reaction, and all that. So they're doing this at the same time to each other in two different directions. So the question then is, why is the moon not crashing towards Earth? This is a tremendous amount of force, and it's one that, if you actually calculate the moon's acceleration from that force, you get like 0.1, 0.2 meters per second squared, 0.02. Which isn't a lot, but that racks up over time. So why is the moon not falling towards Earth? That's why we're using this as a segue. That's what we're going to talk about next week. It's because of rotational motion. But that's next week. Rotation is its own weird kettle of fish. So talk about that then. How does these concepts and this formula by itself feel for right now?
It didn't say too hard.
Okay, good to know. You could use this same formula here to figure out like the force that the moon is pulling on you. If I was to plug in my own mass of approximately 100 kilograms, probably get like 2 newtons. So it doesn't affect me all that much, but it does affect the oceans. It's a small but meaningful effect on the tides. Plus, the ocean has more mass than me, so that's why it is worse. So, questions, comments, concerns, needs, etc.? Yes?
Hey, so if I plug that equation into my calculator, when I need to, when I click to get the answer, would it give it in scientific notation, or would I have to put it in a different book?
Odds are it would default to scientific notation, because I found that if the answer is higher than like millions or billions, it defaults to scientific notation to save space. Like mine auto gave me scientific notation for both of these answers, because it just saves space and time calculating how many zeros to use. So I wouldn't think you need a separate mode. All right. Have a good weekend. Stay dry and comfortable, and I'll see some of you for lab, and the rest of you on Monday. Have a good day.